Okay, start பண்ணலாம் sir.
Okay, so very good evening to everyone for today's session. Uh, the previous session we covered about the different types of glass, fire rated glass, where to use what kind of glass, etc. And other guest speakers also discussed on the structural aspects of glass selection. In today's webinar, we will be covering about the different aspects of high performance glass, the different parameters that are there, and we will also get a deep insight into what are these performance parameters and what do they mean, right? I'm just starting the presentation. So here we are seeing that different aspects are there. First is the thermal properties, next is the visual properties, then the acoustic properties and the aesthetics. So the flow will be like this, four different aspects of the facade glass selection. First, we will go through the thermal properties. So we all have heard of this factor called as the solar factor. We know that there is sun on the outside, and imagine there is glass. So when the incident solar radiation comes in the form of infrared energy, it is incident on the glass. So there are three possible reactions. One is it transmits some percent of the energy. Second, it reflects some percent of the energy, and third, it absorbs some percent of the energy. So when it absorbs some percent of the energy, it starts re-emitting inside and outside. So when it starts re-emitting inside and outside, so if you see what all has come inside, your direct transmitted energy and your re-emitted energy. The sum of that divided by the incident solar radiation is your solar factor. I'm just repeating, solar factor is nothing but the ratio between the directly transmitted plus re-emitted energy and the incident solar radiation. So it is like a ratio. It has no unit. And this gives you an idea of how much is the energy that is directly coming inside your building. Like from the sun we are getting radiation, how much percentage of it is coming inside. If I say that the clear glass, 6 mm clear glass, it has a solar factor of 0.82. And when I go for a coated glass, its solar factor can be as low as even 0.19, which means almost 81% of the heat gain is reduced by this coated glass. This is for an example I am saying. So this is solar factor. Next is the U value. So today, assume that outside the temperature is 35 degrees. The summer has already started. It can range between 35 and 40 degrees here in Chennai. And inside, if you are in an AC room, you will usually keep the temperature at 24 to 26 degrees, approximately 25, let us assume. So 35 minus 25 is 10 degrees difference in temperature. So in this 10 degrees difference in temperature, heat moves from the outside to the inside. So how much is that amount of heat is the question. So how do you answer that? There is a property called as thermal conductance of glass, which is nothing but the U value. So it gives you how much watts of heat passes through 1 square meter of glass when there is 1 degree change in temperature. I am repeating, how much watts of heat is transferring through the 1 square meter of glass and when there is 1 Kelvin difference in temperature. So if you see the unit of U value, it will be in watts per square meter Kelvin. And this gives you an idea of the heat that will come when there is a 1 degree change in temperature. If it is 10 degree change in temperature, you multiply the U value by 10. So this is for 1 square meter. So if there are 100 square meter on your facade, you multiply that value by 100. So this will give you amount of indirect heat gain. So the previous slide we saw about the direct heat gain component, which is a solar factor. Here we are seeing about the indirect heat gain component, which is the U value. So there are two components with respect to the heat gain. So how do you reduce this U value? There are multiple aspects. So first is that when you are using a single glazed unit, its U value is 5.7 watts per square meter Kelvin for a clear glass. When you make into a double glaze, you introduce a 12 mm air gap, it becomes a 6126 DGU. From 5.7, it will become 2.8. Further, if you want to reduce, you can either keep increasing the air gap, but beyond a point, it will not decrease the U value. So 2.8 can become 2.5 if you increase the air gap from 12 mm to 15 mm. Beyond that, if you want to further reduce it, you have to introduce a coating, which is nothing but a low E coating that is done on the glass. What is this low E? It is a low emissive coating. When the emissivity is low, your U value will also be low because they are all dependent parameters. And further, if you want to reduce, you have also increased the air gap. You also introduced the low E coating. Beyond that, if you want to reduce it, you have to introduce a argon gas, which is an inert gas, which will further reduce the U value. So from 5.7 with low E coating with increased air gap and argon, you can even bring it as low as 1 watts per square meter Kelvin. That is also possible with today's technology. It depends on the quality of the coating, what type of coating you are putting, and also what is the thickness of the air gap. Beyond a limit, that will also not reduce. So you are introducing an argon gas. So these are all the techniques by which you can reduce the U value. How to reduce solar factor? It is by different types of coating on different tints. So that is how we can reduce the solar factor and the U value. Why do you want to reduce the solar factor and U value? So let us see the impact of solar factor and U value. So I told you during the solar factor slide that it is a direct heat gain, and the U value is like an indirect heat gain. Why do I say U value is indirect heat gain? Is during the daytime you are getting infrared radiation from the sun. So in the night time you are not getting that infrared radiation from the sun. Still, there will be a temperature, ambient temperature on the outside, and some residual radiations will be there. Some heat will be there on the outside. That heat will still come inside your building because you are maintaining a low temperature using your air condition, or inside you are maintaining a lower temperature. So heat transfer happens in the night time without the presence of the sun also. So this is the indirect heat transfer. Here, if you have a lower U value, you will get a benefit of cutting down the heat coming inside. If you observe in fully glazed office buildings, if they switch off the AC, or if there is a current shortage, in the morning when you go and switch on the AC also, it takes a lot of time to cool down that area because of the heat that has come inside. So this is one area where if you use low U value products, the amount of heat coming inside can also reduce. So this is during the night time and also during the daytime. Whereas your solar factor is very important in terms of the daytime heat reduction. So if you see here, there is an incident solar radiation from the sun which is falling on the surface of the glass. I multiply it with the solar factor. So how do I know how much is the incident solar radiation? It depends on the location. It depends on the building orientation. By meaning building orientation, whether it is the north facade, east facade, south facade, or west facade, and what location is it? Is it in Chandigarh? Is it in Chennai, Hyderabad? That also has an impact on the amount of radiation from the sun. So this you can get from softwares like Ecotech, Rhinoceros, Grasshopper, etc. And you can actually also get it from the internet, but it will be approximate. So this incident solar radiation, let me assume it is 415 watts per square meter. If my glass has solar factor of 0.8, then 0.8 into 415, that will be the amount of direct heat coming in. That is the direct heat gain component. Let us come to the indirect heat gain component. As I told you, let us assume 10-degree difference in temperature, and U value is 5.7. So 5.7 into 10, that is 57. That is the amount of indirect heat gain coming. So this is the total heat gain, which is sum of direct heat gain plus indirect heat gain. So let us see some cases just for easier understanding. I am assuming that the incident solar energy is 415 watts per square meter, and the temperature difference is 8 degrees Celsius. Outside is 33, inside is 25. Okay. So now let me take a clear glass. Clear glass has solar factor of 0.85 and U value of 5.7. 0.85 into 415 is 354. So look at the direct heat gain component. It is 0.85 multiplied by 415, right? That is 354. You see the indirect heat gain component 5.7 into 8, which is 46. So 354 plus 46, 400 watts per square meter is your total heat gain. Right? Next, coming to your solar control glass, like which uses a coated glass, offline coated technology you have. So through this technology, you are achieving a solar factor of 0.4. So when you are achieving this 0.4 solar factor, 0.4 multiplied by 415 gives 166 watts per square meter, and 5.7 into 8 is same. So the U value is not reduced. Only the solar factor I am reducing. Look at the impact it is making. From 354, it becomes 166 directly. U value remains the same, so the indirect heat gain remains as it is in 46. So the sum has become 212. The next slide, if I'm next product, if I'm going, the solar factor is 0.25 and U value is 1.6. So here it is very critical that you select a glass depending on the application of the building. If you are going for a 24/7 operating office, you should go for a low solar factor and low U value. If it's going to be a residence, it's enough even if you go for a solar control product which has only low solar factor. And if it's a hospital, you should go for products with low solar factor and low U value. So this kind of products, it's for high-end buildings, high-rise buildings. where operation is for 24 hours and it is critical to reduce the amount of heat gain, direct as well as indirect heat gain. You just observe the numbers, 0.25 into 415, I'm getting 104. 1.6 into 8, I'm getting 13. So this put together, I'm getting 117. From 400, you can bring it to 117 by investing in a glass which has solar factor of 0.25 and U value of 1.6. This kind of product, properties you can get in single silver and double silver low E coated product. So this type of products will give you this high performance, which will they are actually you have to invest a little more compared to a normal glass, but you will get it in terms of payback. How much is the heat is consuming? It is going to go down, and how much AC load is going to be consumed, that will also go down. I'll explain that in the next upcoming slide. So here I have considered a building, G plus 10 building, 18,000 square meter glass area, and I have assumed all the other factors as constant. The cooling set points, the occupant density, and then the lighting power density, and then the construction wall U value, roof U value, window to wall ratio, the cooling COP, how much is the efficiency of the HVAC, that I have taken as 3.5. And I am analyzing a building in Chennai, and I have taken the ASHRAE 90.1 occupancy for office. I've considered all these as constant. Only thing I'm going to change is the glass property. So here there are different glass variants. So you may ask that if its U value is only important, then I'll just reduce the U value. So if that is the case, I have taken a clear glass as an example. Okay. Next, I have taken few products which are coated glass, and these coated glasses I have chosen carefully such that the VLT is similar. If you see the VLT, it will be 46 to 50% in the same range. This is like different generations of product. ST150 is a product which is a second generation. The next product KT is like a fourth generation. SKN is like fifth generation. So by generation, I mean the performance will be better. Why do I say the performance will be better? If you see in the second product, 46 VLT, 47 solar factor. Observe that ratio. The next product, 47 VLT, 0.38 solar factor. The solar factor is going down. 50 VLT, 0.28 solar factor. And 47 VLT, 22 solar factor. So these are actually giving you a hint, like in the similar VLT range, you can achieve a better solar factor, which means that there is a factor called as selectivity. Light heat ratio, which is nothing but VLT by solar factor, that selectivity ratio keeps improving as you go for a better product. So if you see the third product is better than the second product, the fourth product is better than the second product, and fifth product is better than the second, third, and fourth product. So like that, as you go to the next generation of products, the solar factor goes down at the same level of VLT. So that is the possibilities you have with offline coated technologies available today. So these are all the different glasses I'm considering for the analysis. Let us see the results. So I am calculating the cooling load. So I use a software called Design Builder, which works based on Energy Plus. So here, when I use a clear glass, it's energy performance index, which is nothing but the energy consumed per square meter. So here I have considered only the cooling load. In EPA, you have different components. Here only I am considering the cooling load per square meter of floor area. So if you use clear glass, it is 102. When I use a better coated products, it is actually improving. From 102, it is going as low as 67 and 62. It is almost 34 to 39% savings in cooling load compared to a clear DG. So usually when you run these simulations for energy analysis, you will have to take a base case. So here I have taken a clear DG as a base case just to explain the impact of coating. But usually you will have to take a base case of ASHRAE 90.1 standards, which will say what is the solar factor U value to be considered when you go for a particular type of building and location. So this is just to show you how much is the impact in cooling load you are actually getting. Almost 39% reduction in the amount of money you will be actually paying for electricity bill through AC. And there is one more, indirect benefit. Cooling load reduction is a direct benefit. Here it is an indirect benefit. It shows how much is the heat gain. So if you are sitting near the window, you will get some heat. If it's going to be a clear DGO, how much heat? 187 kilowatt hour per square meter. That is the amount of heat that is going to hit you when you sit near the window. When I go for different coated glasses, these are all different coated glass products. When I go for it, it is actually having lower solar factor and lower U value. So this impacts your amount of heat gain coming inside, the total heat gain. And you look at the percentage reduction. It is going as low as 75% and 83%. When you go for low solar factor as well as low U value product. So I'm just going back one slide. So if you observe, uh, out of 400, we just saw that the amount of cooling reduction you will actually get when you go for different products with lower solar factor and lower U value. But in clear glass, if you observe for 400, 354 is actually due to the solar factor. So if you actually reduce the solar factor itself, a lot of benefits you will be getting. And additionally, if you also reduce the U value, further benefits you will be getting in terms of the heat gain reduction. So this actually is what is impacting over here. The solar gain reduction is reduced because of the lower solar factor and lower U value. So that is about the thermal properties. Just to summarize, the solar factor, U value are two different, uh, parameters. Solar factor is for direct heat gain, U value is for indirect heat gain. You will have to consider a glass which actually has a optimal solar factor and U value in order to get a reduction in your cooling load and your heat gain coming inside your building for thermal comfort. So this is about the thermal properties. Coming to the visible light transmission. So light is also equally important. We are India. We are having a lot of light, correct? So when we are getting light, if you just see at my background, you are seeing some window. So this window is actually it lets in diffuse light. So it is a frosted glass. It lets in diffuse light. So in terms of coating, if you use a coated glass, you can also control the light transmission. The products that I showed you earlier, like different ranges of products, with different types of coating, you can control the light transmission. But what is this light transmission? Light transmission is the percentage of light that is actually coming inside your building. So when I use a glass, imagine the outside lux is some 10,000 lux. The inside I just need 300 to 500 lux. Be spread across the floor area. So to achieve ambient an optimum amount of light inside, the ambient light should be controlled. How do you control it? Using your glass. So this glass actually acts like a inter layer in between the outside lux level and the inside lux level, and it transmits some percentage of the light inside. So this percentage of light is your light transmission. So how much amount of light you have outside and how much has come inside, that ratio, the percentage of light transmitted inside is your light transmission. When I say VLT is 80%, it means that the glass will look rather transparent when you see from the outside to inside. When I say that the VLT is 30%, it will not look as transparent, number one, but which is a good VLT, you may ask. Like, is 30%, don't you think 30% is too low? Might be your question. So it depends on the window to wall ratio. When you have a higher window to wall ratio, even a 25 to 30% light transmission is good enough. When you have a lower window to wall ratio, you need a higher light transmission. So it's like inversely proportional. Yeah, so you have to see how much is the window to wall ratio and how much is the light transmission. How do you do it? You can do a simple daylight analysis and see how much is the lux level coming inside your floor. And usually when it comes to light transmission, there are a lot of myths that if I go for 30%, my room will look too dark. Let us see a few points. So usually when you design the building as architects, you want your building to look like this. So anyone would like their building to look beautiful, right? But end of the day, after the occupants occupy it, the sad reality is that it looks something like this, right? Because occupants will need some visual comfort. They put down blinds. If you are using the wrong glass, you let in what is called as excessive light, right? And here is some examples. When you are choosing for a climate like India, where we have abundant light, when you go for very high light transmission glasses, you want it to look very transparent, then you end up seeing blinds only from outside. So we call it as blinds that blind. I've just done a small case study. So here there is a small office room that is modeled with a window on the right side. So over here you can see that the lux levels are going as high as 7,000 and 7,100 lux on the working table, which is some 700 mm from the floor. And on the right side, I have done the same simulation, but I changed the VLT. Instead of having 60%, I have done the simulation with 25%. And you can see that it is within the range of 300 to 400, lux. So this will actually shows that it doesn't mean that you need to go for 50% VLT or 80% VLT whenever you're having facade in your glass in your facade. So you will have to do an analysis and see what is the right amount of lux level and choose the products accordingly. Some softwares you have for analysis, we have Radiance, which gives you some insights into how much will be the lux level at different points. But to use Radiance, you will need a modeling software like Ecotech or SketchUp, which will actually give you an idea of how the geometry is, how the floor area is, how much glass is there, and if I use different VLT, how much will be the light entering inside. Rhino is also a software you can use to model the building, and you can use Grasshopper with tools like Honeybee and Ladybug to run this simulation. They all use Radiance in the backend. So clearly there is a paradox. What is daylight and what is glare? How much light is comfortable and how much is uncomfortable? So it all depends on what is called as our visual comfort. So our visual comfort depends on our eye, where we are sitting, and the light source that is there. And if the light source is going to be your facade, if the contrast ratio goes beyond, say, actually a thumb rule goes beyond 1:10, you start feeling some visual discomfort. So that is what we call as glare. So to avoid this, you will have to choose the glass depending on the window to wall ratio, and VLT becomes a very important factor over here. So how do you reduce this, excessive visual discomfort? Is by active elimination and passive elimination. There are two techniques available. Active elimination is by using blinds, shades, and shutters, and passive elimination is by design choice and design selection of materials. So when it comes to blinds, we saw that a lot of buildings you will be have to trade off on the aesthetics from the outside, but you will still get some comfort, some percentage of comfort inside. And to avoid blinds, you can go for a dynamic glass. I'll also talk about dynamic glass in the next session. So that is another option that is there to eliminate glare. The other passive, elimination is by using of shading device, reducing, the glazed area. But you will have to see if you are reducing the glazed area, you are also actually restricting the amount of light coming inside. So rather a better choice is to go for glass that has an optimal VLT, and this optimal VLT will not give you glare, at the same time lets in the required amount of daylight. To find that balance, you'll have to do the analysis. And two solutions that are there is coating done on heat absorbing tint, coating done on body tinted glass, like a green tinted, blue tinted, bronze tinted glass. If you do a coating, they actually prove to be better in terms of visual comfort. And second is doing a ceramic frit, like a particular pattern you can print on some portion of the glass, and you can actually get diffuse light inside. So that is another option of getting, reduction of the visual discomfort. So when you do this coating on tinted substrates, you also get, aesthetics from the outside. Usually there is a belief that if I use a particular coating on tinted substrate, my entire space will look dull, or it will look a lot of, my facade will not look good. So these are all some examples where products used with coating done on tinted substrate are actually giving a good look outside and on the inside. So here the product used has only 30% VLT. Look at the amount of light that is coming inside, and it is a coating done on green tinted glass. Still, it looks as neutral as a clear glass. So if you can have a look at the facade, this is one example. This is one more example. You can see that the space has a lot of white. In spite of having a coating done on tinted glass, it is not actually, giving a green tinted look on the white. So it's just a misconception that whenever I go for a tinted glass, everything will look not a location. In India, you can use a coating done on tinted glass, and you can still get ample amount of light, provided you will have to do the analysis and check whether it is sufficient enough or not. So tinted coatings done on tinted also comes with some additional benefit. It also has a low UV transmission. So this UV transmission is important when you have the color of the fabric that is there near the window. So it starts fading. When the UV transmission is lesser, that fading gets reduced. If you have a dark gray when you purchase that particular sofa with the fabric, it will start becoming light gray over some 7 8 years. When you use a coating done on tinted glass or lamination glass with coating, this actually reduces the UV transmission. So this is another way to reduce the UV transmission, which will delay this process of color degradation of fabric. This is another additional info. So next parameter. So we saw about VLT, light transmission, and how window to wall ratio and light transmission are important. And we also saw the advantages of going with choosing the right VLT. When you go for the right VLT for the right building, you will actually get visual comfort. You will get daylight instead of glare, and you can actually do a lot of analysis to understand what is the right VLT for my building. And we also saw the advantages of going for coatings done on tinted substrate. So that is another thing that you can actually observe. So VLT is a very important factor when it comes to selection. Apart from the aesthetics, like how transparent it looks from the outside to inside, it also matters how much light comes inside and how your occupants are comfortable. That's about VLT. And next we go on to the other chapter, which is acoustics. So here, what is the point of having a very beautiful looking building? You are getting visual comfort, thermal comfort, but there's a lot of noise, right? So that is also another comfort you need to consider. So on the screen, you're seeing two standards, BS 8233 and NBC. NBC is our National Building Code. We have a 2016 version that is available. And the BS 8233 is another standard that is followed. So both here, they are actually discussing about how much should be the comfortable decibel level inside your space. So if it's going to be a dwelling, it can be 30 to 40 decibels. It is going to be educational, it can be 40 decibels. With an office room, it can be 40 to 45 decibels. So these are all some of the examples. To achieve this 40-45 decibels, and you say that you have a noise on the outside, say 70 or 75 decibels, your wall, your frame, and your glass. So when it comes to the wall, you will have to know what is the performance of the wall in terms of acoustics. If you're going for a brick wall, if you're going for a aerated block, what is the acoustic reduction, which is the RW, the weighted average noise reduction factor. You should also know what is the weighted average noise reduction factor of the glass system that is used. So based on a combination of this, you can actually determine what is the noise level required to be reduced by the glass. So that is actually RW. So today we have a lot of acoustic consultants who do this analysis, who measure what are the different frequencies of noise outside, what is the noise level on the outside, and we know, by that, we know that how much is the noise level to be maintained inside. So based on that, we can calculate what is the noise level to be reduced by the glass. So when you derive at that, and glass manufacturers usually give these reports, RWC and CTR. RW is your weighted average noise reduction factor. C is your high frequency correction factor. CTR is your low frequency correction factor. I'll give some background to this. I'll just spend a few minutes on the slide. So if you see how the manufacturers do the tests, uh, we actually have a noise source, we have the glass in between, and we have a noise receiver. So when the noise source emits noise levels in different frequencies, the glass is there in between. The glass has the different reduction in different frequencies, because depending on the frequency, the reduction will vary. At higher frequencies, it can be 30 decibels. At lower frequency, it can be 25 decibels also. So there is a range that is set. So who sets this range? Say 100 to 3100. This range is set by standards like ISO 717 or ASTM. So there are standards for calculating the weighted average noise reduction. So I take ISO 717 part 1, which gives me how much will be, how to calculate the noise reduction factor, which is RW. So I have a data of different reductions at different frequencies. Say 50 hertz, it reduces, the glass reduces 35 decibels. 100 hertz, it reduces 34 decibels. Like that, I measure for the different bandwidths and I calculate a weighted average. That weighted average is RW. Say, for example, the 6 glass, the RW is 32, which means on an average, it reduces 32 decibels in that particular frequency bandwidth. And if I go for a higher frequency apart from that bandwidth, you will have to use a correction factor. So there are two correction factors. One is a high frequency correction factor, which is C, and there is a low frequency correction factor, which is CTR. So for high frequencies noise sources, you will have to use RW plus C. If you take 6 it is 32 minus 1, which is 31 decibels, will be the reduction in high frequencies. In low frequencies, it will be 32 minus 2. RW plus CTR, which will give you 30 decibels. This is the amount of reduction you can achieve. One more concept you need to observe is when you go for DGU, doesn't necessarily mean that it is acoustically superior. It gives you better performance. You have to choose glasses with different thicknesses. If you see 612.6 reduction, it is 30 decibels, and 612.5 reduction, it is actually 32 decibels. If you see from 6 mm to 8 mm, when you increase the thickness, actually RW is better. But here, even when 612.5 is there, your 612.6 is not as good as your 612.5. Reason being, you have to choose glasses with different thicknesses. Instead of, if you go for same thickness, the concept of resonance happens. Because whatever frequency the first 6 mm has reduced, same frequencies only your second 6 mm can also reduce. So what happens? Resonance happens, and your entire performance of the acoustic performance of this DGU goes down. To avoid resonance to happen, you should choose glasses with different thicknesses so that you can achieve a better RW. So this is the concept of acoustics. Whenever you go compare different types of glasses, lamination always fares better in acoustics compared to DGU with different thicknesses. And you can also go for glass with higher thickness in single glazed. So in terms of economic aspects, a single glazed higher thickness with some coating actually will end up to be economic compared to DGU of the same thickness. Right? So these are some value engineering you can do when you do select glass for your building. So we saw about acoustics. Next comes the aesthetic part. So we all know that glass has internal and external reflection. Even if you take clear glass in single glaze has 8% internal and external reflection, and DGU double glaze unit has almost 15% internal and external reflection. So when you go beyond a certain limit in the reflection range, you can see a reflection of yourself when you see from the window. So you should keep it as low as possible. So when you choose glass with a lesser internal reflection, you can actually have a better connect with the outside. So that is one benefit that you get. So when it comes to internal reflection, when you're comparing 3-4 products, glass with a lesser internal reflection gives you a more benefit in terms of connect with the outside. So while choosing glass, you can consider that for your facade. External reflection is purely your design intent. If you want the glass to be fully reflective from the outside, and your external reflection has to be higher. And there are also products which have lower external reflection, which have a subtle look. Those products are also available. So it totally depends on your preference and your design intent. So external reflection gives you an idea how reflective the glass will be from the outside. So we saw different aspects. I come to the end of my presentation. Thermal properties, solar factor and U value. The visual properties, VLT. Acoustic properties, RWC and CTR, and aesthetics, the internal and external reflection. So these are all different factors you need to consider while selecting glass for your facade. So in case you have any queries, you can raise it, I can handle it. In the next session, I'll be also dealing about how these glasses can contribute in green buildings. I'll get into detail on IGBC, Griha, etc. But this is the end of this session. Thank you so much. Hello. Hello.
Hello, sir.
Sir, அவ்வளவுதான் ஓவர் சார்.